This video, an interesting problem here to prove. If X and Y are column matrices in Rn, that means they have one column and there's an entries in this column. Then it turns out that the trace of XY transpose is equal to X transpose Y. Maybe it's not necessary, but the first thing I would do is look at the size of these results. The results of this product and this product. Well, X is n by 1. Y is n by 1. X transpose is then 1 by n. And Y transpose is 1 by n. So what is X times Y transpose? What is the size? Well, n is n by 1, and we are multiplying this by Y transpose, which is 1 by n. Those two entries are the same, so the answer to the size will be the outer values. It will be an n by n matrix. Okay, this is an n by n matrix. Interesting. Now, X transpose Y better be a real number. Better be a 1 by 1 matrix, because the trace of our matrix is just the sum of their values or elements on the diagonal. You add up finite real numbers, you get a real number. And the number 7 is a 1 by 1, is a 1 by 1 matrix. You can think of 7 as a matrix. Now, X transpose is 1 by n. I have that right there. And I multiply this by Y, which is n by 1. And those two numbers are the same. That means the product of X transpose and Y, the product of those two matrices, is well defined. And the size is the outer number, 1 by 1. Which is a real number. So just making sure that everything makes sense. I take it you didn't need to do any of this, but it's just good to see. Okay, so now what is X? So let X be x1, x2 up to x sub n, and Y be y1, y2 up to y sub n. And what will xy squared be? I meant to say xy transpose. Well, it will be x, x1, x2, all the way up to xn times y transpose, which will be y1, y2, up to yn. And when I multiply the first row by the first column, I get x1, y1. And when I multiply the first row by the second column, I get x1, y2. When I multiply the first row by the last column, I get x1, yn. When I multiply the second row by the first column, I get x2, y1. The second row by the second column, and then eventually the second row by the nth column. And then I go down to the nth row, and I multiply it by the first column, and then the nth row by the second column, all the way down to the nth row by the nth column. And I would just love to put trace in front of this, trace in front of this, trace in front of this, And then the trace is just the sum of the elements on the diagonal, which is x1, y1 plus x2, y2, all the way down to xn, yn. So I have exactly what the left side equals. Let us see what x transpose y equals. X transpose y, well, here's x transpose x1, x2, up to xn times y. I take that back. I wrote down what x equals. X transpose will be x1, x2, up to xn. And I multiply that by y, which is y1, y2, up to yn. And there's only one row and one column. When I dot those two, when I multiply those two, I get x1, y1 plus x2, y2 all the way down to xn, yn. And those two are equal. That is, I can go from here to here to here to here to here to here. Okay, this equal sign is surely valid because what I just boxed certainly equals this. There's the end of the proof. This theorem has been proven. As always, if you enjoy seeing videos like this, please subscribe to my channel. Leave a comment in the comment section if you have any comments to leave, and most of all, watch and learn.